So recently I've been conducting system design interviews for junior developers, and I keep on noticing the same pattern. When we got to the database design portion, a lot of candidates will say something like, I don't want to split this into too many tables because joins are slow. And when I try to dig a little bit further into why joins are slow, they can't explain it. They just mention that they heard it from someone or read it from somewhere. So my understanding is that join is not necessarily slow. It's the table scans that's causing joins to be slow. So I thought it would be interesting to demonstrate this in Postgres database. I'm going to walk you through 5 lessons I learned from working with databases, starting with the very basics of just querying a single table all the way up to using multiple joins to fetch data from the database. Also going through how indexing and filtering would help with improved performances. So we're just selecting everything from the reviews table where the title is equal to review 101. And in this case, we'll just run this query to analyze it. So if I hit run, you can see that on row 4, we're doing a sequential scan on reviews table. Sequential scan here means that we're scanning the table row by row. And another important detail here is loops. And in this case, loops is 3. So that means we're doing 3 iterations here. And in each iteration, we are removing rows we're removing about 3 million rows here. So this means that if you multiply this value by 3, that's about like 10 million rows. So in this case, to fetch a single item here, which is review 101, we're basically doing a full table scan. And after that, we're basically removing pretty much everything that's in that table other than the review that we want. So that is very inefficient. And you can see the execution time took about 266 milliseconds. So if we go back and try to add a index on the title of the reviews table, and when you run this query, it's going to take a while because we are adding an index to 10 million records, and it needs to restructure into a tree structure. As you can see, this took 11 seconds to do. Once that's done, let's rerun the same query again and see what the results are. Now it's using the index scan, using the index that we created on the reviews table. Right now, it fetched a single record, and also it only looped once. In this case, the execution time is significantly better than before. It only took 0.074 milliseconds this time with the index. The reason that this scan is so fast, in the reviews table, the title field has all unique values. This means that this field title has high cardinality. So the next lesson, we will look at a field on the reviews table that has low cardinality. In this case, I am looking at the reviews table, looking at the ratings field. So if we just first show the distribution of the ratings field, you'll see that we only have 5 different ratings. If you look at this row 5 here, pretty much 90% of the ratings are a 5-star ratings. And this is about 9 million records here, right? We have 10 million total reviews, and 9 million of them is a 5-star review. So if we go back here and try to select all the 5-star reviews here, we'll see how this performs with no index. And you see that this took about 1,000 milliseconds, and that's 1 second. It did a sequential scan on the reviews table, fetched about 9 million rows of data. It only has 1 iteration, and this is filtered by the ratings equal to 5. And as you can see, the rows removed by the filter is about 1 million, and this makes sense, right? Because we have 10 million reviews, 9 million of them is a 5-star review, and 1 million of them, which we removed, is the other reviews. Okay, and this took about 1 second to execute. So now let's add an index to see if this will improve our performance. Okay, and that took about 3 seconds to run to create the index. Oh, and we're creating the index on the ratings field. Okay, so now let's run the same query again to retrieve all the 5-star reviews. And as you can see, this took 1.1 seconds, 1100 milliseconds. So basically, the performance didn't change. And why the performance didn't change even though we added an index. And the reason is because the cardinality of this field is very low. We only have 5 fields. Therefore, if we look at the output again, therefore, even though we have an index on the field itself, in order to retrieve the 5-star reviews, we still need to scan through the 9 million records of data since the review is skewed towards 5 stars, right? Therefore, the database decided this time that we're not gonna use a index scan since that's not gonna be any cheaper than just using the normal sequential scan. Therefore, the query plan is exactly the same as before when we didn't have any index. Okay, so now you may think, say if we do want to still fetch data from the ratings field that has low cardinality, how can we improve the query performance? And to do that, we need to basically combine the low cardinality field with a high cardinality field, like the titles field. This way, when we do a query, we'll be able to first scan through the high cardinality field, and then within those results, we'll fetch all the related low cardinality fields. In this case, we'll just go through this query one more time. So this is fetching the 5-star reviews, and this took about 1.1 seconds. You can see it in row 9, and now we are fetching the titles from the reviews. That's equal to reviews 101 here, and you can see that's 300 milliseconds. Okay, so let's not add an index now. We're not going to add an index for now. And now we will try to combine the 2 fields and see how fast this is. So basically we're doing a select to get all the 5-star reviews, from user 42. Okay, so we'll see how fast this is. And you can see this is about 300 milliseconds, right? Which is a significant improvement from just fetching the 5-star reviews themselves, right? Let's see if this can get improved by adding an index. And before we do that, let's just look at the output real quick. So we did an index scan using the user's P key, which is primary key on users. So in MySQL databases, the primary keys are always auto-indexed, so we don't have to manually index them. And then we're doing a SQL scan on reviews, filter by user ID equal to 42. And you see the row removed by the filter in each iteration, which we have now loop is 3 here. So in each iteration, we're removing about 3 million rows of data. We're matching about 32 rows of data in each iteration, right? So this is our bottleneck here, the sequential scan on the reviews table that uses the foreign key user ID equal to 42 here and ratings equal to 5, right? Because each time we're basically doing a full table scan, but we're only fetching 32 rows per iteration. Now in this case, let's try to add a index. In this case, we know that the ratings index is not gonna do much to the performance. So let's just add this anyways to see what the result is. I'll just add the ratings index on its own to see if it would change anything. Okay, so I added the index on the rating field, and we'll run the query to see if anything improved. You can see that it's still around 300 milliseconds. So it didn't improve much, or in this case, it didn't improve at all, right? Because we're still doing a sequential scan on the reviews. Now let's add an index on the user ID. User ID is unique, right? So that means it has a high cardinality. In this case, this should improve the performance. So we'll add the index, and it took 4 seconds to add that index. Now let's run this one more time. And you can see that the execution time right now went down to 0.2 milliseconds. And you can see we are doing, again, scanning, index scan using user's primary key. And right here, we're doing a bitmap heap scan, which is faster than the sequential scan, but it's not the same thing as index scan. And I won't get into that right now. And in here, you'll notice that it's filtering by right here, it's filtering by the user ID, right? Using the index that we created on user ID. And you'll notice that, we only have a single loop, and in that single loop, we're just getting all the data that matches user ID equal to 42, which is 101 rows of data. And, that took 0.2 milliseconds, which is a huge performance improvement. Okay, so the last lesson 4 here, we will demonstrate some queries using joins. So basically this query is we're trying to get the order information related to this user ID, okay, 42. And we're basically joining, all the tables together so that we can fetch all the related data on that user. So if we go back to the data output one more time, so you'll see that in here, we're doing a sequential scan here on 3 million rows of data for the table order items. And same thing here, sequential scan on orders table. In this case, we're filtering by the user foreign key user ID equal to 42. And in each iteration, there's 3. In each iteration, we're only getting 246 rows of data back, and we're removing about 300,000 rows of data, right? So this sequential scan is our bottleneck, and we can add indexing to basically improve the performances. So if we go back and if we add these index one by one, in this case, we will add an index on the user ID foreign key on the orders table. So we'll do this. First off, let me double check. So yeah, this is 657 milliseconds. So we'll add the single index first, and then run this query. The execution time didn't improve much. However, let's see if we got rid of the sequential scan, one of the sequential scans. And you can see here, instead of earlier, it was sequential scan on orders table. Now it's bitmap heap scan. And in this case, we've got 739 rows of data in each iteration, right? And in here, we are doing the scan using the index that we created. And you can see here, index scan using the product primary key on product. So yeah, this here, so this index, that it didn't seem like it improved our performance here. Let me just look at it one more time. Order user ID, orders user ID. I'm actually not sure why adding that index there didn't improve the performance, but I'm going to move on and create another index. And if anybody know why that one didn't improve performance, please let me know and leave your comment below. Okay, so I created another index on the foreign key order ID on the table order items. So let's run this one more time to see if that improved anything. Okay, that significantly improved the performance. Now the execution time is 15.6 milliseconds. Okay, so I believe this was the one that we were looking at. Index scan using the index we created on the order items. Okay, it scanned 10 rows of data, looped 739 times. So therefore, it fetched 7,390 rows of data. And now we have one more index to create. Okay, that took 4 seconds to create. So let's run this one more time to see if that improved any performance. Okay, creating that index did not improve any performance. And as you can see, even though I created the index, but it still used sequential scan on products. And okay, and looks like rows is only 1,000. So earlier in the video, I said that the products table has 1 million rows of data. However, I was wrong on that. Turns out it only has 1,000. And this is why, even though we added an index, it didn't really use the index scan because there's only 1,000 rows of data and it's not really worth the cost to use index to do the scan. And that's it for my video. To sum this video up, joins are not necessarily slow. It's how much data you need to scan in your joins that will determine join or just query in general is slow or not. Thanks for watching. See you next time.